Lesson 8.3, working with y equals ax squared plus c. Recall from our last unit, when the coefficient, that's the number in front of the x squared, when that's positive, it means the parabola opens up. The opening is at the top part of the parabola. However, if the a value, that's what we call the coefficient in front of the x squared, if the a value is negative, then the parabola opens down. We're going to match these equations with the graphs here. Notice that some graphs are narrower than others. Do you remember why? Why some graphs are narrower than others? That has to do with the a value. So the a value not only tells you if the graph opens up or down, if the a value is, let's say it's greater than 1, we won't talk about negatives yet, but if it's greater than 1, it gets wider, the bigger it is. And if it's between 0 and 1, a value is between 0 and 1, then it starts to get narrow. Okay, look at these graphs here. Our first one is x squared minus 7x plus 10. So what do we know about that when we look at it? Well, the easiest thing, this is in standard form. Standard form means there's no brackets, it hasn't been factored. Easiest thing to identify is the y-intercept. This y-intercept is going to be a 10. So right away, I've only got one option here. But let's look at some of the other features. In front of the x squared, I've got an invisible 1 here. Since that's a positive, that means it's going to open up and it's not going to have any kind of stretch or compression. It's going to be normal width. So that's my red one right here. So let me just put that underneath. I'll write red there. I'll just put a 1 right here. The red graph is 1. Okay, let me erase this. Next one, equation 2, y equals 2x squared plus 4x minus 6. Again, standard form. So let's look at this time the y-intercept is a -6, and you can only tell that when there's no brackets, when it's in standard form. Y-intercept of -6, well, there's only one right here. But let's double check. So the black one has a y-intercept of -6, but let's check the a value here. The a value is a positive 2. It's positive, that means it's going to open up, which the black graph does, open up. See how the arrow, it would be here, it's opening up. And it's a little skinnier than the red one. Compare the black one to the red one. Imagine if we were able to pick it up in line, put the vertex of the black one right on top of the vertex of the red one. The black one would be skinnier, and the 2 does that. The 2 makes it skinnier. So equation 2 is definitely the black graph. Equation 3, this is only a binomial. There's only 2 terms here. It's still in standard form because there are no brackets. But I'm missing that last number that was really helping me identify the graph by the y-intercept. So there's no constant here. Here we had a constant of -6, that's your y-intercept. Here we had a constant of 10, that's the y-intercept. Here I don't see anything. That means the constant is actually a 0. So which one of these have a y-intercept of 0? So I look down my y-axis until I get to 0. It looks like it's going to be the orange one. But let's just check. At the front of equation 3, we have a negative. So that means my graph must open down. Does the orange one open down? Yes, it does. So imagine always arrows at the ends of these graphs. So the orange one opens down and it has a y-intercept of 0. So this is equation 3. How about equation 4? Equation 4 has a y-intercept of -16. Let's find that on here. -16. There's -16, and it looks like that kind of grayish blue colored graph is going to be our graph, but we'll double check. The -2 in front tells me that it opens down, and it's also a little skinnier than the red one. The red one is our normal width. So is that true? Is the blue one opening down? Yes. And is it a little skinnier? Yes, it is. So the blue one is our equation 4. And the last one, equation 5, is again a binomial, but we do have a constant here. The constant is a positive 14, so that's, remember, the constant is always the y-intercept. So let's go and look at the y-intercept right there. It looks like it's going to be the green graph. Let's double check with the a value. It's negative, so that means it should be opening down. Is the green one opening down? Yes, it is. The opening is, it's going down here. And it's a 1/4, and the 1/4 part, the negative part means the opening down. Let me put the arrow right there. That's the negative part, means opening down. The 1/4 part means it will be wider than the red one was, and it is. So that means the green one is equation 5. Summary. When the a value is positive, the parabola opens up. The parabola opens up. That means the vertex is at the bottom. That means the vertex is on the bottom. And when the a value is negative, the parabola opens down, which means the vertex is at the top. Opens down, and that means vertex is at the top. So that's like the orange one right here. The orange one right here, the vertex is at the top. There's a vertex, and so it opens down. When the a value is between 0 and 1, when the a value is between 0 and 1, so that's like, scrolling up here, that's like this one that we just did. That's my a value. So the sign we've already taken care of when we're talking about opening up and down. So the a value between 0 and 1, whether it's positive or negative, the a value between 0 and 1 means the parabola is wider, or the parabola, what we actually say for that is it's a vertical compression. That's a little difficult to explain over the computer, but it means that if you had a parabola like this, and vertical means up and down, right? That's vertical, like if you jump vertically, you're jumping up or down. So vertical, so imagine that you put a hand down here at the bottom and you put your other hand here at the top, and you're squeezing together, you're squeezing vertically. That's going to make this get pressed out wider. So the parabola is wider, and what that, a better way of phrasing that you'll see is vertical compression. I'm not going to be able to fit the compression here. P-R-E-S-S-I-O-N. That's a vertical compression. But the larger the a value is, then the skinnier the graph is. The skinnier the parabola. And a more technical way of saying that, again, if we take, let me just draw another graph here. I'm going to draw one down here. If we have, let's say this is the regular shape. This is an a value of 1. And this time, instead of squeezing down, imagine that you're grabbing the tops of it, and you're kind of pinning this down here. The vertex is not moving. You're holding that still, but then you're pulling. You're vertically stretching. You're pulling it up. That's going to make it skinnier. So that's called a vertical stretch. Important here, what I have in the box, there's two parts of the a value. There's the sign of it. That's when the a value is positive or the a value is negative. And there's the value of the a value. So the a value could be between 0 and 1, or the a value is bigger than that, 2, 3, 4, 5. So there's two important parts of the a value. Here's our whole equation when we're talking about the a value. Specifically, the a value is really what the front of this page is focusing on, the sign and the actual number itself. So far we've talked about quadratics in standard form, so no brackets. X squared plus bx plus c, no brackets here. And that's all we did today, but previous lessons we've talked about factored form, that's when we have the brackets. Now we have this, this is also standard form, the one we're talking about today because there's no brackets, but it's missing this middle piece. It's got just the ax squared and the c. It's missing that middle piece. It's still in standard form, but it looks a little bit different. Example 1, for the quadratic relation y equals 1/4 x squared plus 6, determine the y-intercept and whether or not the vertex will be the maximum or the minimum point. Do not graph. So we'll start with the y-intercept. Remember what the y-intercept is? The c value, that's the constant. The c value has no x with it, just a number. The constant is just a number. That's your y-intercept. So this is my y-intercept. Y-intercept is, and I'll write it as a coordinate. Y-intercept has an x value of 0, and the y value is a 6. Now, is the vertex a maximum or minimum? So the vertex, okay, does it open up or down? This graph right here, does it open up or down? Well, there's a negative in front. Negative there. The negative means it opens down. So if it opens down, is the vertex a maximum or a minimum? Remember we talked about that here? So if the parabola opens down, the vertex is at the top. If the vertex is at the top, then we're talking about a maximum. So vertex is a maximum since the parabola opens down. Opens down. And the question says, it says we don't have to graph it, we just had to figure out if the vertex would be maximum or minimum. So I'm going to do a little sketch here. You don't have to, but let's say this is 6 there. So our y-intercept is a 6, and it opens down. So it's going like this. So the vertex is definitely a maximum. Example 2, a rock is dropped from a bridge. It falls to the water surface according to this relation. This is an equation that's telling us how the rock is falling. H is the height of the rock above the water, measured in meters, and t is the time after the rock is dropped, measured in seconds. So if I took this equation and I said, well, where's the rock after a half a second? Well, then I'd plug in a half here, I'd work it all out, and I'd get the height after a half a second. What is the H-intercept? So that's the same as a y-intercept, except because I don't have a y here, I have an h, I have to say the H-intercept. What is the H-intercept of the relation? Remember what that is? That's the constant. That's this number here. And what does it represent? So the H-intercept is, we'll write it as a coordinate. So that's at times 0, that's what it means. You have a 0 for your x, we get a 50. And what does that mean? So if the time, this is time here, and this second number is height, so at time 0, meaning at the very beginning, before the rock is dropped, it has a height of 50 meters. And you're probably used to calling that initial value. So the initial value means like the starting point. Complete the table of values for the relation. Round your answers to 1 decimal place. So we have a decimal here, which means we're going to be using decimals in our answers. Think first of reasonable values of t for time. So let's talk about that for a second. Reasonable, whoops, that's supposed to be a highlighter. Erase that. Reasonable values for t. So I need to put some numbers in here. And we're talking about a rock being thrown from a bridge, dropped from a bridge into the water. So how long do you think that would take? Let's think of some good time numbers here. How long do you think it would take to hit the water, a rock, from a 50-meter high bridge? Well, it's probably not going to take 60 seconds. It's not going to take a minute. 50 meters is high, but it's not that high. So our first t value should be 0. We're not going to put any negatives in here. We're starting at time 0, and we already know what the height is there, actually, right? We already know. I'll sub it in later, but so how many seconds do you think it would take? Well, it's probably not going to take more than 5 seconds. So let's do 1, 2, 3, 4. Let's see how far we get it. 4 seconds is pretty long in terms of something dropping from a bridge. So let's see how that is. Now we have to sub in. So we already know this answer, but I'm going to show you anyway why this is true. So I'm taking the original question up here, but instead of t, I'm subbing in 0 squared plus 50. So that gives me a height of, so 0 squared, this is going to be 0. 0 times 4.2 is 0. I'm getting 0 plus 50. So there's the 50 that we already knew the answer was. So that's our first coordinate is 0, 50. What's the next coordinate? For the next coordinate, our t value is a 1. So let's sub in a 1. Negative 4.2 times 1 squared. 1 squared is easy. So 1 squared is 1. So this is turning out to be just negative 4.2 times 1. So I'm just going to write negative 4.2 plus 50. And if you want to get out your calculators, you can. So negative 4.2 plus 50, or 50 minus 4.2 is giving us 45.8. So at 1 second, the rock is 45.8 meters above the ground. So remember, it started at 50. So the first coordinate we have here is 0, 50. Times 0, we're at 50. At 1 second, our coordinate is 45.8. Well, where's the rock after 2 seconds? Now, this isn't linear, which means it's not just going to be the same distance below again. This is quadratic. Negative 4.2, sub in a 2. 2 squared will be a 4. So that's negative 4.2 times 4 plus 50. So you can do that in your calculator. Do this part first. Negative 4.2, because of the order of operations, we have to do that first. And then add on 50. Get 33.2. So this coordinate, after 2 seconds, the rock is 33.2 meters high. How about 3 seconds? Negative 4.2. So we're always going back up to this original equation, in case you're wondering what I'm doing here. I'm taking this equation. Negative 4.2, putting in a 3. So what's 3 squared? Remember, we have to do the 3 squared first. We can't do negative 4.2 times 3. So this turns into a 9. What do we get for 3? We get 12.2, getting closer to the ground, of course. So at 3 seconds, the stone is only 12.2 meters high above the ground. Let's see what happens at 4 seconds. Negative 4.2 times 4 squared, that'll be a 16. Negative 4.2 times 16. So remember, we have to do the multiplication first. We'll get negative 17.2. That's a negative now. That's the first negative we've had. So at 4 seconds, the rock is negative 17.2 meters above the ground. What does that possibly mean? It doesn't make sense for this question. If this question were not a word problem, specifically about a rock hitting the ground or anything hitting the ground, if it weren't a word problem, it would be fine. But it is a word problem, which means we're not going to be able to graph this number because we can't. This number right here is h, right? This is all h. We can't have a height of negative 17.2 unless we're drilling into the ground or unless we're going below sea level. We can't have this number. So this one we won't be graphing. Part C says graph the relation, label axes properly and carefully. So I'm only going to put my y-axis right here really close to the edge and the x-axis as well, because with most word problems we don't deal with negative numbers. All right, along the bottom here, this is my time axis here, and we're measuring time in seconds. I've got 0 to 4, so I'm not just going to go 1, 2, 3, 4 like this. I'm going to spread it out a little bit. 1, 2, 3, 4 seconds. Now my vertical axis is h, and that is representing height. And my height numbers are, I've got a 50, that's the biggest one, and then I go down to the negatives. So I just want to make sure to fit a 50 on there. 5, 10, 15, 20, 25, 30. I can count by fives, but I'm going to label every second one. 20, that line should be, they should be landing right on the axes, right on the grid lines. 40, 50, just put another one up there, 60. So height, I should have put here, height is being measured in meters. Now we're going to, so we've labeled our axes properly and carefully, and now we're going to graph the relation. My first point is 0, 50 right there. My next point is 1 and 45.8. Again, these are, when you get decimals, they're really hard to put on. 45.8, I'm counting by 5, so it's just over this 45 line, like that. 2 and 33.2, so 2 and 30, there's 35, 33.2, let's put it about here. 3 and 12.2. 3 and 12.2. Around there maybe. Now 4, it was negative 17, so I'm not going to put 4 on there. I can see it's got to have a quadratic shape. I know that because there is an exponent of 2 in my equation. It's got to be quadratic. It is quadratic, and the shape has to be a parabola. So this right here will be my vertex, 50, and the reason I know it's my vertex is this new form we're talking about today with the, scroll up here, this form, when we just have a binomial and we're missing the x squared, the x term in the middle, your y-intercept is always going to be your vertex. So I know this is my vertex, and I know it comes down. I'm going to draw it coming down. Actually, let's look at this part D here. Estimate based on your graph or table of values. How long did it take the rock to hit the water? So that's what's going to happen when I draw my graph and it's going to hit somewhere here. That's going to be my estimation point. At some time between 3 and 4 seconds, my height will be 0. That's when it's going to hit the water. This intercept, this is the initial height. This intercept is the final height, which is 0. So I'm just going to put a little sketch on here, and we don't know the exact, oh, that should be curved. We don't know the exact value. So you're drawing your own graph there. It should, mine's not very smooth. Try to make it smooth. And this point right here is going to tell us how long did it take the rock to hit the water. So using your graph, what do you think that is? If I look at my graph, I would say it's about 3.3 seconds. So that's going to be my estimate. I estimate it will take about 3.3 seconds to hit the water, and that's estimating based on, you can use a table of values. The table of values tells me it's somewhere in between 3 and 4, because here I had a positive and here I had a negative. So my table of values told me it would be in between these two numbers. But I really used my graph. I looked at my graph to see when it would hit the t-axis there. So that's an estimate. But the next question here, the last question, is saying calculate it. Calculate the x-intercept to check your answer for D. Sub in h equals 0 and isolate t. So this is telling me what to do. Sub in h equals 0 because I want to know when my height is 0. So I'm kind of crowded here. I'm going to write this on the side. My original equation is h equals negative 4.2 t squared plus 50. but I know that the height has to be 0 to find out when it hit the water. The height is 0. So negative 4.2, I don't know what t is, so that's what I'm trying to find out. So we're going to isolate t. First thing I'm going to do is subtract 50 from both sides. Subtract 50. That gives me negative 50 equals negative 4.2 t squared. Now what do I do? I'm trying to isolate t squared. I'm trying to isolate t squared first, and then I'll isolate t. I'm going to divide both sides. I have to break that negative 4.2 off of the t, and the only way I can peel it off of there is by dividing both sides by negative 4.2. So you're getting out your calculator here to do this. 2 negatives will make a positive, so my answer is going to be positive. Round to 1 decimal place, we have 11.9, that's rounded, equals, so these have canceled, and I'm left with t squared. Now, how do I get rid of a power of 2? I need to isolate t. To get rid of the power of 2, the opposite of squaring something is the square root. So I'm going to take the square root of both sides. That will cancel out the power of 2 with the radical. Now, if you left the original number on your calculator here, which was 11.9, and it had a whole bunch of digits after it, and you just take the square root of that directly on your calculator, I think you're going to get 3.45. If you rounded it and then you just used 11.9, you're going to get 3.449. So they're both really close. So I will just put down 3.4. 3.4 is t, and the question asked the it said x-intercept, really. It should have said t-intercept there, not x. Calculate the t-intercept to check your answer. So what we have found is the actual exact answer is not 3.3, it's 3.4, but we were pretty close. Therefore, t equals 3.4 seconds when the rock hits. Okay, so that is practice working with equations that have this form: y equals ax squared plus c. So normally there's a plus bx in there, but it's plus c. It's still standard form. And remember, an important piece is that that's your y-intercept. And that's always an easy part to graph quickly and to get going on your graph. That's it. Do lots of practice and let me know if you have questions.